Hello, everyone. I'm going to talk about my the research, the areas, what I'm focusing on. And the title is Analysis of Pathology Musculoskeletal Dynamics and Developing Smart Assistive Device to Improve the Functionality for People with Disabilities. So my research evolves around identify the characteristic of the walking patterns of the people with disabilities, such as neurologically impaired, like cerebral palsy, stroke, and also I'm interested in doing analysis of people who got amputated, like losing their limb, like mostly the lower limb. And because trying to understand these dynamics helps us to develop a new type of assistive device and help us to develop a guidance to control the device optimally to improve the function, the walking, the maximally. So my research topics are highly interdisciplinary because we integrated deep learning algorithm, human motion analysis, and sensors, as well as computation modeling. So I'm going to dive in a little bit more detail. So the first project is to develop a musculoskeletal model of the lower limb amputation, because now the lower limb amputation, after they got surgery, and then actually it is unclear what's the best way to provide rehabilitation exercise and what is the best the characteristic of the prosthesis to help people and modulate in terms of considering the affected muscles. So it is really important to have the computational musculoskeletal model, because this musculoskeletal model helps us to predict and build the strategies to provide subject-specific the rehabilitation exercise, as well as developing advanced the prosthesis. But in order to do that, we have to identify what is the characteristic of the muscle. So now we are doing the multiple muscle experiment using the ultrasound and the human dynamometer, electromyography, and also we are gathering the information from MRI, so that we are building the muscle model of the amputees. And then with this model, then we actually bring the participant in and then do the analysis, how they muscle behaves walking with different, the type of prosthesis or different walking patterns and so on. So after we find out, what's the role of the residual muscle, like affected muscle of the amputees, then we can do a lot of things. For example, how the muscle strengthening exercise of the residual muscle impact, the better results of the rehabilitation exercise, and how this muscle interplay with the other the assistive device and so on. And the next topic is about the people with people for the neurologically impaired individuals. So, for example, the stroke survivors or children with cerebral palsy, they have different muscle control. For example, the contracture, the tight and short muscles are the really common, and usually they prescribe ankle orthosis, which is the plastic piece of the boots. And then it applies the stiffness so that the musculoskeletal system interplays with that type of that level of stiffness, so that they can alter their kinematics as well as alter their muscle function. So current standard of care prescription method is a certified orthotist. They set the one specific stiffness, and then they evaluate with their naked eyes. So they just evaluate with their the visual inspections, and then they just arbitrarily tune the stiffness. And then once they think this is okay, then they release the patient. So but the problem is this is highly subjective, although they follow some certain rules, but the prescription may not be optimal to improve the walking, and as well as the restoring the pathologic muscle pattern. So what we're trying to do is we're developing a platform which is, changing the stiffness automatically, so that we can provide the instant the level of customized stiffness to the patient, so that the patient can improve the walking function dramatically. And in order to control find out what is the subject-specific optimal stiffness, we're using the machine learning algorithm and also the musculoskeletal study, so that we're trying to find what is the optimal stiffness which can improve the walking function, as well as provide rehabilitation exercise in step-by-step living daily basis. That means that when people have optimally tuned assistive device, then they also can do the muscle rehabilitation exercise. That means they can go less to the clinic, so that they can save time and money. And in this study, we are also incorporating the nanomembrane sensor, because this type of device covers the most area of the muscle, so that this compliant the electromyography sensor allows us to collect the signal from the muscle. And the next step is more towards about the people with lower limb amputation. And again, people with lower limb amputation, they lost their the major muscles, which is the calf muscle, to which plays a really important role of walking. And then they usually prescribe a single passive prosthesis. But the single passive prosthesis cannot provide optimal energy releasing, so that they have to recruit extra musculatures to compensate a normal walking, and that results in increased metabolic costs, fatigue, and less mobility. And the other question, the concern is, since they have to accommodate with a single variable of stiffness, they can't accommodate with the variable walking scenarios, because when we are walking outside, we are obstructing a lot of walking scenarios, such as level walking, incline, decline, and so on. So actually, we are using visual feedback. So we are we are seeing the obstacles and identify what are the walking conditions. And then we immediately control our muscles to accommodate the different walking conditions. But current prosthesis doesn't have and only relies on the internal sensors. And then they have to several steps to identify, okay, what is the specific walking conditions. And then now the device can return provide some feedback. So to solve this issue, we integrated the video camera, so that it senses the environment, so that this device can identify, okay, so what is going to be the obstacles and walking conditions, so that it can provide the instant the feedback. And also, this platform allows us to provide the optimal energy releasing, so that they can fully utilize the energy recycling mechanism of the passive prosthesis, so that they can walk more optimally. And as well as, usually when we collect the motion and kinematics, we are using really expensive motion capture system. You might see it in the animation industry. People attach, the shiny little things on their body, and then the many cameras are, the collecting the trajectories, the markers, so that people can calculate what is the joint angles. And since this process only allows us to validate in the level walking, just the flat surface walking, so that it cannot test the various walking conditions. So we are integrating IMU sensors and the video cameras to and then using a machine learning algorithm to quantify what is the joint kinematics and kinetics and so on. And because these technologies are really useful for the patient, because this allows to the real time, this allows to identify the motion and the torque of the joint in a real time, so that this information automatically sends to the clinicians, so the clinicians can monitor or without the meet the patient in person. And also the clinician can give us the medical feedback instantaneously. And the last thing is it's about the Rca integration. So as you can see here, there are largely two different types of surgery for the amputees. One is just socket fitting, and the other one is Rca integration, which is integrating the prosthesis directly to the bone. And this is fairly new type of procedure, but the problem is, I mean, there are some advantages compared to this the procedure, because usually people have a lot of skin disease and inflammations and swelling the limb due to the vacuum pressures. But this one is directly to the bone, so that people doesn't no longer hassle with the skin disease. But on the other hand, this procedure may cause some serious the consequences, such as the bone fracture. So it is really important to find how we can tune the device to minimize the bone fracture. Otherwise, they have to go back to the surgery again. So in order to do that, we are using the musculoskeletal model, which I presented the earlier slide, and then we also can integrate the responses of the force plate, the prosthesis, because we don't know what is the optimal stiffness of the design of the prosthesis, which can minimize the stress level of the residual bone. So this study also allows us to collect the motion outside the lab, as well as we came up with the novel type of variable stiffness, the prosthesis, which is inspired from the marine animal, like the mantis shrimp. And then we combine these all informations to the finite element analysis and testing out when specific the stiffness is given and how we can minimize the stress concentration on the residual bone, so that eventually we can protect the participant from the very really aggressive, even aggressive exercises. So my near-term research plan is, now we are building the platforms such as the devices which can alter the semi-active the variable stiffness ankle orthosis, prosthesis, and also we are developing the technical basis with the how we can identify the human motion outside the lab. And in the long-term plan is we want to actually recruit the multiple participants and to do rigorous of testing to see how our new device and new the algorithm can actually give the benefit to the individuals. And I'd like to thank you to my the collaborators, and these are my the lab members. And I'd like to take any questions you have.